specifically looking at a particular way of describing the error we have when we're talking about our learning processes, right? So we specifically looked at this term, which we considered to be sort of the error of our estimator f hat conditioned on some value x. And we did some analysis to basically break that down into two terms. One, the irreducible error, right, caused by stochastic noise, right? It's just the difference between the true label and this eta x squared. And eta x was considered to be sort of this best case estimator one could have. And then on the other hand, right, and that irreducible error was something we really didn't have a lot of control over, right? That's something having to do with sort of the fundamental shortcomings of doing prediction in this setting, right? There's some randomness in y relative to x. And then there's this other term, which we described briefly and called the learning error, right? So that's the difference between eta x, this sort of really great predictor that one might be able to construct in some settings, but not others, and f hat of d, which is the predictor we're actually going to construct as a function of the training sample d, right? And we mentioned that this learning error can be caused by any number of things, either using too simple of a model or the fact that we don't have enough data to learn that model accurately. Okay, so now what I want to do is actually do some manipulation of this learning error term, right? I just copied this over from the other slide, right? And in general, the way we start all of these analyses is we start by adding and subtracting the same term, right? And doing some simple completing of the square, right? So that's just equal to this term right here. And then if we want to argue, this is this 2ab term here, right? If this is a and this is b. If we want to argue that 2ab is equal to 0, we can certainly do that. And I actually recommend that that be something you all work out, although I'm happy to come back to it if we have a bit of time at the end. But arguing to yourself, especially using, I'm giving you a bit of a hint here, using the fact that the expected value over the sample we draw of f hat of d, I would recommend calling that f bar of x. Okay, so I'm not going to work that out, but there's a very nice analysis you can do just to show that this middle term should be equal to 0. Great. Okay, so when you show this middle term is equal to 0, right, then the entire learning error term can be described as a squared plus b squared, okay? And this first a squared, we often use the term bias squared to refer to that, okay? And the intuitive reason for that is it captures some amount of the difference between sort of what we'd like our estimator to be producing for x and what it's actually producing for x in expectation. Right? And b squared, right? If we look at b squared, it's measuring some amount of reproducibility or stability of our estimate of f of x.
Oh, hi, teacher.
Yeah.
There's some display issues, and can you check the chat to see the issues that all of us share? Like there's some issues with display. Yeah.
Okay. Let me see. Sorry. Okay.
Thanks.
The slides are torn up. Screen sharing. Okay, so the screen is sharing, but the slides are. Apologies. Kevin, do you see? They're kind of broken up. Kevin, how do you see the slides? Or do any of the TAs? It's a little, oh, it's just a little of the bottom part, okay. Okay, so there seems to be something wrong with the screen sharing. So let me try something else, okay? I'm going to stop this screen share and I'm going to try again. Apologies, guys. Okay, let's see if I can. Thank you for letting me know. I appreciate it. Okay, one more second. Okay. Okay, does that look better for people if I click here? Can you see the screen correctly now? I see one yes in the chat. Yes? Oh, good. Thank you, everyone. Good. I don't know what was happening there. I was doing a screen share and I was doing it the same way as always. I just restarted it. Okay, well, I'm glad that's working. Okay, so what were we talking about just a minute ago? We were talking about sort of this nice separation. If we look at the learning error, we can manipulate it into basically two terms. One of which we call the bias square, which looks at sort of how much our estimator's expectation is off from a to x, which is a sort of idealized estimator of f of x, and the variance of our estimator, right? And the variance of our estimator we'll talk a little bit about throughout the remainder of class, but that's somehow trying to capture how much our estimator would vary if we redrew the sample and trained it again. Okay. So the reason we got to talking about all of this is that we were talking about linear regression or polynomial regression, and we were trying to talk about sort of whether large p or small p has better properties in various ways, right? And a majority of you said small p seems to be doing a better job than large p, with the intuition that we were seeing overfitting for large p, and we were generalizing as well as we would have been for small p, okay? And so if we look at this, right, the variance term in particular, the variance term is asking if we redrew our data, right, if we didn't start with the pink dots, but we started with the, sorry, if we initially started with the pink dots, but if we imagine redrawing our sample from the same distribution, we might get the purple dots rather than the pink dots. If we get those purple dots and we imagined redrawing this orange line, which represents the least squares estimator for large p and small p, we might want to know sort of how much our estimator f hat would change. Right? Okay, and I have a very quick, seems that that's not going to work. Okay, I have a quick poll for you. Okay, so I can find it. Okay. And I want to ask, let's see. Okay. So when we were talking about this before, people were talking about basically there being two, let's see, chat, here we go. Okay. So if I activate this poll and then okay. So I'm asking everyone to fill out this quick poll, which is just asking whether we expect small p or large p to have larger variance. Okay. And people seem to be able to look at that. So initially, right, about 10 of you have filled it out, so I'm gonna let it go for just another second. Okay, so the question I asked was, which of large P and small p I would expect to have larger variance, which is this question of, if I redrew my sample, right? Imagine I ran a least squares, I computed a least squares estimate on a sample, and then I redrew that data from the same distribution and made another computation of the same least squares estimator. Do I think small p or large P would have larger variance in that regard? I'm going to let this keep going because it's nowhere near, small p and large P are not all that far apart at the moment. About 60 of you have answered, and you know, the answers are fairly different. So I'm going to let it go until we get to at least 100 people, because we're now at 70. Okay, 30 more of you should answer. Okay, so right, so if we're looking large P and small p, right, the variance is measuring how much we'd expect our estimator to change if we redrew the data and computed the least squares estimator again. Okay, and now it seems that we're getting a bit of spread between large P and small p. Okay, and what I see right now is that there are 80 people who've answered. 82 people have answered. 52 people are saying that the large P estimator would have higher variance. Okay, okay, good. Now I have another poll that I'm going to ask you to also answer. It's at the same link in 1 second. I'm just going to activate it. Okay, now I'm asking about bias, okay? So the first question was whether large P or small p we would expect to have higher variance. And now I'm asking about bias. Okay, and you guys have good intuition. Oh, wow, these are not as far. Again, I'm going to give you another second to let this settle. So 60 of you have answered so far, and it's about 1/3, 2/3, to give you some sense of where we're at. Okay, okay. So this bias term here is just looking at sort of how far off we are from fitting our data, right? And now it looks like we've stabilized a bit, and small p is beating large P by about a factor of 2, right? And that's correct, right? We would expect small p to have higher error than large P on our initial sample. Okay. So, right, in general, if you look at mapping out the complexity of the class of models that we consider, which will be more formal about complexity throughout the remainder of class. You can sort of think about complexity as a monotonically increasing measure, right? Certainly if you're thinking about polynomial regression, as P increases, you're thinking about more and more complex models. And as you increase the complexity, you allow yourself to drive your bias to 0, but your variance goes up, right? And if you're looking at this entire term and considering this entire term to be our learning error, right? Or at least these two parts, right? We might want to try to trade off bias and variance to get this nice somewhere fairly low on the total of bias squared and variance. Okay, so this is intuitively what is generally meant when people are talking about bias variance trade-off. Okay, so if we talk about linear least squares, right? And I want to just give you a brief example of walking through sort of, oh, I see a hand. Yeah.
Yeah, could you like reiterate, I understand the variance part, but could you reiterate like how you were like interpreting bias? Like, yeah, it's not, I guess it's not clear to me like how you are able to like connect the fact that like smaller p has larger bias.
Yeah, so what, yeah. Trying to think of the right way to describe this. So let me get back to that question after we walk through this on linear least squares, if you still have the question. Is that all right? Great.
Yeah. Can I offer a possible explanation?
Absolutely, yeah.
So like in, like for instance, like let's say the true data, let's say, you know, this data that we're observing is drawn according to, say, a 7-dimensional polynomial plus noise, okay? Well, let's just say that's the true model that this data is being drawn from. Now, if I use a p=3 model, so a 3-dimensional polynomial, I will never be able to fit a 7-dimensional polynomial or a degree 7 polynomial with a degree 3 polynomial. And so that means that, like, I will always have some amount of bias because my model is not complex enough. My 3-degree polynomial is not complex enough to fit the assumed true 7-degree polynomial. And so that is bias. It's that, like, even the best model in my class, the best 3-degree polynomial can't fit the 7-degree polynomial, and that isn't going to incur bias. So typically we think of bias, you're having non-zero bias when a simpler model, like when your model is too simple, it cannot actually, it cannot represent the true underlying function that generated the data. And now the issue is that if I did a 10-dimensional polynomial, okay, now I might have 0 bias because my polynomial is complex enough. A degree 10 polynomial can represent a 7-degree polynomial, which we assume is the truth. But by having an extra amount of flexibility, by adding in that 8th, 9th, and 10th degree polynomial, I'm incurring extra sort of variability. And I might fit noise with that extra variability, and that might incur extra variance.
That's right. Right. Yeah, and one thing that this image maybe doesn't give you some sense of is, right, we would imagine that as our complexity approaches the complexity of the underlying data generating process, that this decrease in bias would sort of level off. Yeah. Okay. Great. Does that help? Thanks, Kevin.
I'm sorry, could you also like repeat what's the intuition for the variance side? Like why the variance like increases, the P increase, just some like sort of intuition.
There are various intuitions. I guess trying to think of one of the easier ones. So one of them is that there are simply more parameters of the model to estimate, right? And for a fixed data set size, if we're increasing the number of parameters we're going to be estimating, right, the sort of error bars around each of them that we're going to be able to draw will be wider. There are other explanations as well, but that's maybe a simpler one than some of the other ones we could talk about. Okay, great. Okay. So, right, so this is just giving some intuition that as we increase model complexity, we see our bias squared decrease, but our variance increase. And if we care about this total error description that we've drawn here, we really care about both, and we care about balancing them, right? So there's a trade-off. Increasing complexity decreases bias, but increases variance, and we care about this nice sum of the two. All right, so if we wanted to talk about what bias and variance look like for linear least squares, right? We can write out precisely what our estimator looks like, right? This is just the term that we computed in the last couple of classes. And if we wanted to talk about the irreducible error of our estimator, right? That just is equal to y minus eta x squared given x equals x. And does anybody want to unmute themselves and guess what this is? What this is equal to?
The variance, maybe?
Yeah.
Sigma squared, maybe?
Yeah. Also, I may have, if you guys have downloaded the slides, you have the answer for that. But okay, good. Okay, so if we actually want to look at the bias of our estimator, right? Let's do that on the next slide. Okay. And apologies if these transitions aren't super good. I've been working on trying to figure out a way to get builds to work better. I haven't figured it out yet. Spent a couple hours this morning trying to figure out if Notability had that ability. Okay, so let's just work on this bias term, right, and ignore the square for the moment. Okay. So if we just write this out, right, eta of x is equal to x transpose w, right? And the expectation with respect to the draw of our sample of f hat of d of x is just equal to this right here, okay? Okay, so then if we just expand our definition of our least squares estimator, right, we get this term right here, okay? So this is just expansion definition of least squares. Then if we want to think about, we can expand the definition of y, right, into this term right here. That's all I've done. And again, I can, sorry, looking at how I did this. Okay, and then I can just expand this out, right? I can actually do this multiplication. Okay. And the reason I'm doing all this manipulation is to show you what the bias is equal to for this term, okay? Okay, so then if I look at this term has something pretty nice, right? Right, we have x transpose x inverse and x transpose x, right? So this term by itself, or this term just goes away. And we end up just with this term here, right? This guy. Okay, so then with a little bit more manipulation, right, we have x transpose w minus x transpose w plus this one additional expectation term. And I want you to convince yourself that this last expectation term has expectation 0. And does anybody have any guess for why that might be true? Yeah, that's right. It's yes, good. I'm seeing some of the, somehow I changed the setup for Zoom and I can sometimes see the things you're putting in chat. Yes, the error is unbiased itself, right? This is all about epsilon having mean 0, right? So that means this entire term is equal to 0 because we have x transpose w minus x transpose w plus something which is equal to 0, right? Which means that linear least squares has bias and therefore squared bias equal to 0. Which is great, right? We hadn't talked about our estimators before and talking about whether they were biased or unbiased. So in the setting that our model, our data generating process is linear, then using a linear model and estimating the error with least squares, we get bias 0. Now we can do something similar with variance, and I'm actually not going to walk you through the calculations with variance, but I do have, I have all of the slides here, so you can walk through them yourself. Okay. But the intuition and the way we do the computation is quite similar, right? And in this case, we show that our variance of our estimator ends up looking like p sigma squared over n, where n is the number of samples we have, and p is the dimensionality of the estimator we're looking at. Okay. Should that be d? I might have a typo there. I will check it after class. Okay. So that's all to say that we've done a computation where we thought about linear least squares, and we were thinking about this bias variance trade-off, right? And in particular, we showed that the irreducible error is a function of sort of how much inherent stochasticity there is in our y's, right? Along with showing that this is an unbiased estimator, and that it has variance that's a function of the sigma squared again, and the number of samples we have, and I think p is actually supposed to be b, so d. So I apologize about that, and I'll make sure that's fixed. Yeah, I see a hand.
So this is going to be a just a tiny notational question because I think I missed something. What is W hat?
Yeah. So W hat is the maximum likelihood estimator, or the least squares estimate.
Okay, as opposed to W, which is the
true linear model that governs Y.
Okay, because I was used to W being the. Oh, okay, this is assuming that this is all of this math here is assuming that the thing we're trying to model is actually linear.
Yep, for sure. In this box.
Oh, okay. I missed. That was the fact that I missed. I thought that we're talking about like linear least about how linear least squares behaves when you throw it at literally anything.
Nope, definitely not, right? Like all of these computations we were just doing assumed that we actually were learning a linear model and that a linear model actually generated our data.
Okay. All right. So that's just okay. That's why W. Okay. Thanks. That makes some of these slides make a lot more sense. Cool.
Okay, great. Now I'm going to hand things over to Kevin. And I think I need to stop sharing my screen.
Thank you.
Yep.
Let's see.
I think I managed to stop broadcasting. So I see another hand too. Do you want to ask
Yeah,
me
let's
or do you
take some
want to ask
questions.
Kevin?
Yeah, so I have a quick question. So is W hat an estimator of W?
Yes.
Thank you.
Thanks, Ed. Any other questions? People, feel free to unmic yourself and just ask.
Could you just quickly? Oh wait, sorry.
Okay,
Go ahead.
maybe it was a bad choice.
Thanks. How can we think conceptually about taking an expectation over a random set?
So that's a good question. You can conceptually think about the way you construct your data set as like drawing each sample separately, right? So you're drawing n samples from a distribution. Intuitively, right, if you think about things drawn from a Gaussian, right, drawing n samples from a Gaussian twice, you wouldn't expect to see the same estimate, or you wouldn't expect to see the same sample, right? But they might both look, for reasonably large n, reasonably like they were drawn from a Gaussian, and in fact the same Gaussian.
I had
Thank you.
Yeah.
I had a quick question. I didn't quite hear you when you said that there was kind of a small error in your slides. Could you just quickly repeat what that was?
I think my P should have been a D, but I'm going to double check that.
Within the variance of the linearly squared?
Yeah.
Okay. And D would mean?
D is the dimension. Yeah,
okay,
that's
same
right.
way as P. Okay.
Yep.
Thank you.
Anybody else? Great.
All right. Then I will take it away.
Great, thank you.
Sorry, can you see my screen?
Yes.
Okay, good. Okay, so hi everyone, good morning. I'm going to do the next couple lectures. And just very briefly, I'm gonna race through the bias-variance trade-off, just so that if I use any terminology that Jamie wasn't using or anything like that, we're just on a consistent thing. They're the same slides, but I don't want to say something that was a little different than Jamie said it, and then like now, even though we're talking about the same thing, you don't know what we were talking about. So again, just like with Jamie, please interrupt me. Or to a hand, and the TAs will let me know. I'm trying a new way of sharing my screen, which seems great, except for now I can't see the chat, which seems extremely problematic. Oh, here it is. Wait.
Yeah, and apologies. We keep the options we have available in Zoom keep changing, or we wouldn't keep changing everything.
Yeah, why? Okay, I'm just gonna go ahead because I no longer see a chat. Okay, I found the chat. That's very exciting for me. Okay. Before I get started, are there any questions? Not so much about the material so far, which I'm going to talk about, but like any questions with the class or homework or grading or anything like that that had you burning questions that you'd like to get an answer to real quick?
I have a quick question.
Yeah.
On the website, it says the homework is due Monday, April 24th, but I don't think April 24th is a Monday.
Oh, okay. Yes, it's due the 24th, not on Monday. I think 24th is a Friday, actually.
Yeah, it's a Friday.
Okay.
Sorry, we'll fix that. Thank you.
Thank you.
Okay, great.
Oh, I also see a question about releasing the LaTeX source for other homeworks. So we should probably discuss that offline unless you have a strong opinion about it, Kevin. I've gotten a couple of emails too.
Yes, we have seen that. So traditionally, we have not released the LaTeX for a couple of reasons. One is because sometimes we borrow problems from other professors, and they have explicitly requested us that we do not release the LaTeX. Simply because if the LaTeX is posted somewhere on our website, it's just really easy for other professors or anyone else to steal the problems. And sometimes, and many professors like to be asked, they like to be emailed and asked, hey, can I use your homework problem? I don't really care. I mean, when I produce materials, I want everyone to use them, and I don't really care about credit or anything. But we do from time to time borrow problems from other people, and they have requested that we not post the LaTeX on some of those problems. It's typically just like 1 or 2 problems from the homework, but that is why we released homework 0, because I mean I made that assignment. But homework 1, there is 1 or 2 on there sometimes, or maybe not even that one, but maybe further other homeworks. But it's just for simplicity, like, so I don't need to keep track of which ones are mine and which ones are someone else's. That's why we've historically not released the LaTeX. I hope you understand. We don't request that you restate the problem. If you just have the answer there, that's totally fine. You shouldn't need to retype the question. But I'm sorry about that. Yeah, Chetan?
Yeah, will we be able to download these Zoom videos eventually, or can we only see them on the Zoom website?
So I have a short answer for that. We were expecting you to be able to download them. However, that ability has been disabled by the University of Washington.
Awesome.
Indeed, the number of times we've gotten mixed answers has been pretty high. So the short answer is not easily. If you have very poor internet connectivity, please contact the course staff. We may be able to find a workaround for individuals, but it's one that we don't feel particularly comfortable with sharing broadly for a bunch of privacy reasons, actually. And that's maybe one of the reasons the University of Washington has disabled that possibility. Right, if you have problematic internet connectivity, get in touch with us and we'll see what we can do.
Okay, cool, thank you.
Okay, I'll go ahead and get started then. Thanks for everyone's patience and understanding during all this difficult time or interesting times. Just setting up some notation. Just like Jane was presenting, we have some x and y drawn from some joint distribution pxy. X is usually your features, say in RD. Y is your label. So y is some other, say, real number here. X is, say, number of bathrooms, square foot, etc. Y is the house price, for instance. Eta of x is this, what we're calling the expected value of y given x. And basically, it is the best predictor of y given x. Okay, it is the best possible estimator you could come up with. And so if we go through this, we find that this best estimator of y given x.
Hey, Kevin.
Yes.
Whatever you're doing to share your slides isn't working.
Oh, that's awesome.
Apparently, we're all going to be having some technical difficulties today. Sorry about that. I guess we both tried something different and didn't work in either case. Okay. Maybe we tried the same thing. We tried screen mirroring. Okay, now we can at least see the slide. Write on it for us. There we go. That's looking good. Okay. That's right. Okay, we can see that.
Okay, good. Thank you. Sorry. Yeah, we're actually trying to improve the service.
Also, there's the additional problem that the default settings in such a large room seem to like not be exactly the same as
right. Our test setup is not the same as the lecture setup, unfortunately. So we're guessing as we go. So yes, the optimal squared error predictor is equal to eta of x, this thing in red, where it's equal to the expected value of y given x. It is the best thing that you could do in expectation. Of course, eta of x is unknown. We don't know what it is. What we really have is for any given x, we have this distribution of y. And so if we take any slice at any particular value of x, there's some distribution over the y's. And this eta of x is really the expected value of y given that particular x. So if your data is Gaussian, this happens to be sort of like where the mode is at the top value, but that's not necessarily true. It could be really anywhere. It's just the expected value of y given a particular value of x. And this is like the best thing you could do in hindsight. Now, so we want to learn eta of x, but we don't have eta of x, and we don't have p of xy. We have samples from p of xy. So we have xi, yi from iid from p xy. And we're going to compute over some function class calligraphic f, or cal f, which I would be calling it. And f hat is some empirical risk minimizer, or basically the f hat that minimizes this loss, this squared error loss that we've been talking so much about. And so what we learn is this orange line, where red is the best thing possible. We see the pink data points, and we learn this orange line that fits through these empirical data points, these finite amount of data. And so what we want to care about is really not how well we do on like training data, but how we do on unseen future data, which is the expected, which is y, a new draw from x and y. And this is what we do, the expected value of y minus f of hat x squared. So the issue is that for any draw of the data, if we see a different data set, because anytime we have a data set, you should think of this as being like a different draw. And for each data set that we see, if on one day we see one data set, the next day we see another data set, the next day we see another data set, we're going to learn a different f hat every single time. Now, we don't get to see all of these, of course. We only get one data set, but this is a nice thought experiment of like, if I did see a different data set every single day, I would get a different f hat every single day. And so there was a question a few moments ago about like, what is variance? How should I think about variance? And what you should think about is exactly what Jamie said, is basically at a particular value of x, when I see these different data sets, I'm going to learn a different f hat on every single one of these data sets. The data set that I have, the one that I observed, I'm going to learn some f hat, but I could have seen any one of these other f hats. They're all equally probable because under different data sets that I could have observed. So the variance of a particular estimator is given a random draw of a data set, how much do I expect that estimate, f hat of x, to vary? You know, and here it would basically be this amount of the variance, when I'm like drawing sort of a confidence interval here, but you don't need to really think about it as a confidence interval. It's just sort of very heuristically or intuitively, it's just sort of the range in which I expect sort of my f hat to differ over. Now, and so that is by definition the variance. How could I reduce that variance? Well, I could simplify my model. What if my model really can only learn just sort of a flat function? So like, what if these are the possible f hats I can learn, just like flat functions? And there, if that were the case, then we might expect sort of, given different data sets, we might have different f hats. These reds could be all the different f hats we could learn. But now they're terrible, right? They're very, very far from the truth, which was this sort of like arc kind of data. But the variance of them is much smaller, recognized by the fact that the sort of difference between the minimum and maximum value at this x is smaller. And this has to do with because learning just a flat function is much simpler than learning sort of this polynomial, this arc-like function. And so variance comes from the fact of like, how flexible are you? How much does your function change or vary from different data set draw to different data set draw? Now, that's sort of the variance. Basically, is describing how much do I expect my f hat to sort of vary. And vary around what? Vary around the expected function I expect to see. So there's so every single data set, I get a different f hat, one of these different orange lines. But now if I take the expectation over all possible data sets that I could have seen, not just the one I saw on this day, not the one that's in front of me, but if I take the expectation over all possible data sets that I could have seen, I'm going to get some function, which is the expected value of f hat, with respect to all data sets I could have seen. And that's what's denoted here in green. It is what I would expect to see, what is the expected value of f hat in expectation over the data sets that I could have seen. Now, this is never observed. We never get to be able to see what f hat of x, the expected value of f hat of x is, because it requires taking an expectation over all possible data sets. And if we had that, if we could do that computation, then we'd know what the probability of distribution is. We'd know what pxy was, and we would never do this in the beginning. We just define eta of x. So, but what it does, it allows us to talk about and reason about the bias and variance trade-off that Jamie just went through. And so each orange line here is a possible realization with respect to a data set, possible f hat we could have learned from different possible data sets we could have seen. And the green, the expected value of f hat is really sort of averaging over all possible data sets I could have seen. And it's never observed, but it's a tool to reason about things. And so Jamie went through this decomposition of the total error, which is the expected value of y minus our predictor f hat. And what it comes down, yes.
So there were two hands in the chat.
Raj, what's up?
If you're trying to answer or ask a question, you're muted, Raj.
Sorry, my bad. It all looks the same at this point, all the buttons. For like your schematic for your linear model, you said that like it would have lower variance. Like for this distribution, how are you like justifying that? I mean, it looks to me like there's like a pretty like how are you saying that it has lower variance compared to your quadratic model?
Good question. So this goes back to what Jamie was saying about number of parameters. So I'm sort of implicitly assuming here that my cal f, my class of functions, these arc-like functions, looks something like, I'm assuming that f hat looks something like f hat of x is equal to some constant a plus some linear term plus some quadratic term. That would create my arc. Now, what this red function is, each one of these red functions, let's call it g hat of x. Each one of these is just a line. So it ignores the value of x, and it's just saying like, oh, it's just like some value a. And so basically f hat is parameterized by a, b, and c. So that's the number of parameters. And g hat is just parameterized by a constant. It's really just learning a single number. And because it's learning just one number versus three, there's sort of less sort of like trying to fit this random data I'm going to see. And so we'd expect sort of, because it's trying to learn less, we expect it to sort of vary less.
Gotcha.
It's kind of like if I simplify what I'm trying to learn, if I sort of lower the stakes, or lower my ambitions on what I'm trying to learn, if it's very, very simple, I can't really miss that bad. If I aim small, I miss small.
Right.
But I could have a very large bias because the line is terrible, but the variance will be smaller.
Yeah. Okay.
Ariel.
Yeah, I had a question about the expected value of the f hat of x.
Yeah.
So you're saying this is a result of redrawing this predicted with different sets of data many, many times, and then taking the expected value of all of these different lines, right?
That's exactly right. So,
So,
yeah,
I
so
guess
basically
on
each
top of
one of
that,
these. So like
yes.
this, I'm calling this one, a single draw D is n draws from PXY, a data set. And now when I say each data set, this was, D1, that makes that one, another D2 makes that one, another D3 makes, that one. And each independent data set will create a different F hat because it will fit to different data.
Okay. So then would it be fair to assume that if we have like increasing amounts of data from 1 to n, let's say our n increases, will we approach this expected value of f hat of x?
That's a really, really great question. So I think to repeat your question back to you, just to make sure I'm understanding it, you're saying this n here, the number of data samples within each data set D, if that gets very, very large, if n goes out to infinity, will each one of these data sets will be very different, but will each f hat basically converge to the same thing? Will basically the variance tighten? Will each, even though you're learning many different, all these data sets are different, but does the f hat learn from each data set sort of converge to one single one based on these n data samples? The answer is sometimes. You would want that. That is a favorable property of an estimator, and we will see that. Jamie actually showed one example of that last time, just a moment ago, where the least squares estimator, the error went down like 1 over n. So that would be true. It would have that property, but that's not always the case, and that's something we'll be talking about later in the quarter.
Okay,
but
thank
that
you.
is absolutely, yeah, my pleasure. Okay, and so this total error in green here, this expected error of our predictions with respect to y, can be decomposed into the irreducible error, which is just like eta of x is the best thing you could possibly learn. It's unknowable, but it's the best possible estimator, and that is going to incur some error. And that's what we call irreducible error. The other part is the learning error. This is how far off are our estimates off from the best estimator eta of x, which is of course unknown. Jamie went through, you can decompose this into bias squared and the variance squared. And so now what we're doing is the bias squared is eta of x, where eta of x is the best possible estimator, minus this expected value of f hat with respect to data. So this is the expected function you'd see over all possible data that you could see. And that is your bias. So that's basically, so when we're looking at like very low or simple models, this is going to be the large term, because this is basically like in expectation, how well is this model not going to fit the best model in hindsight, which is eta of x. And the variance term is basically saying, okay, I know that each time we see a data set, I'm going to get some f hat. And I know that in expectation, there's some expected value of f hat. How much is my f hat that I saw differ from the expected value of f hat? And so that is what the variance is doing. It's not with respect to eta of x, it is with respect to your model. And how much does your model differ from time to time of what data set you see over and over? So there's some expected f hat, and now you have a data set in front of you. You only have one data set. How much do you expect your data set to vary from the expected data set that you could have seen?
And it just occurs to me, I know we're generally being pretty pedantic about our expectations with respect to. One way we could be even more pedantic about this one is we could call data set 1 D1 and data set 2 D2 and be specific about which one we mean here. And that might make this term even clearer, that it's asking about sort of what would happen for data set 1 versus data set 2.
That's an excellent point.
I only thought about it when I saw you present it, not when I myself was presenting it.
Of course, that's how it always goes, right? And so, yeah, so I put little subscripts here where D1 and D2 are IID draws from the same data, so the same size, everything. It's just, this is what we expect to see. And so, as Jamie just concluded, why do we do this? Why do we care about the bias-variance trade-off? We do it to design algorithms, to understand how our error breaks down. Because if you can understand and quantify your error in a model, you can then develop better algorithms that reduce these terms. Because we know that the error in your model, because if you go and evaluate your model on some data set, you come up with some model, you get some new IAD sample, and you evaluate on the model on your data set. Okay, you're gonna get some number. You're gonna get something like, oh, you have 0.68 error. What does that mean? How do I reduce that error? How do I go and adjust my model in order to reduce the error to learn a better model? And to think about that process of thinking, okay, what should I change? We find it useful to think about the error as being composed into 3 different pieces. The irreducible error is something you can't avoid. Maybe if the irreducible error is 0.67 and the error you're measuring is 0.68, you really can't reduce it that much. You're kind of done, and you're doing the best you can. But if the irreducible error is really low, then that's okay. And then you can really reduce these bias and variance. And so the rest of your error, your learning error, is decomposed in this piece, the bias and the variance. And just as Jamie was saying, there is some sweet spot here. We know that as complexity, and we're being sort of vague about what we mean by complexity. We're going to see an explicit example in just a moment. But you can think of complexity as being the degree of the polynomial. Okay, so like if you have a degree 2 polynomial has less complexity than a degree 5 polynomial. Okay, so complexity increases as the degree increases. And just as we were talking about, like if the truth was a 7-degree polynomial, then as our complexity, as our fitted polynomial degree goes up, the bias is going to go down, right? As we get more and more complicated models, the bias will eventually go down. But with having higher and higher complexity models, the variance is going to increase. And so your total error, your total learning error, is the sum of these 2 pieces. And so what we want to do is learn, have some trade-off, or basically find an algorithm or find a learning, tune your algorithm so that you're basically balancing these 2 bias and variance pieces. And so to conclude, we want to minimize the total error, the sum of the bias and variance. We can often not measure the bias and variance directly, but we can think about it. And the point here is that with respect to complexity, your total error has this U shape. If you're very, very simple, you have very high error. As you increase complexity, the error goes down. But then if you're too complex, the error starts going up again. And then this is the sort of intuition that we want you to be sort of to have and think about algorithms. So when you're developing some algorithm and you're getting some error, you have some sort of insight into knowing, okay, well, how should I change my algorithm in order to reduce, maybe it's too biased, or maybe the variance is too high. And then you can reason about how should I change my algorithm in order to reduce one or both of these parameters. So any questions on that section? And all of that was review, so apologies. It's just one of the most fundamental concepts of this course. So like, I hope you'll forgive me for going over it again after Jamie just went through it, just because it is, I don't think it hurts to see things a couple of times. I know it takes me I have to see a talk a couple of times before I can really grok it.
Professor, a quick question.
Yeah.
So for bias, as the complexity increases further, why is it always decreasing? Intuitively, I feel like similar to variance, shouldn't bias also increase after some point?
So, and I do want to mention, like, this was something I briefly said when I was sharing my slides, right? If we think of complexity as something that, like, sort of our true data is generated by a degree 7 polynomial, and our complexity, we could bring it out to a degree 7 polynomial or even beyond. You could imagine the bias might go up again, but or at least level off. I think it's, yeah. I'll let Kevin say more about that. But.
Yeah, I mean, these are cartoons. Okay, in real life, they don't always behave this nicely. There's not. It's very hard to say like the bias always decreases with complexity and the variance always increases. That's not actually true. But generally that is what's going on. And what we want to instill in you is basically the intuition. It's not wrong intuition, but like on any particular model class, like linear regression or whatever, or deep networks, you might have different behaviors. There might be some wonky things that deviate from this like very canonical model of as complexity increases, the bias always goes down monotonically and the variance always increases. These are principles that are generally true and good guiding intuition, but like you will be able to find counterexamples. But like this is sort of like 101, and then like when we, if you want to get more advanced in machine learning, you can start talking about, well, where does this model break? What regimes in which this is just the wrong way to be thinking about it, but this is generally the right way to think about it.
Yeah, so I understand that, but like I'm confused about like why is it? What's the reason behind this counter behavior between like bias and variance?
Okay, so right. Oh, you're saying, you know, why as complexity increases, why does bias go down and variance go up?
Yeah, I thought they would behave the same way.
Right. Okay, so as complexity goes up, bias is going to decrease, because if the truth was a 7-degree polynomial, then as a higher and higher degree polynomial, you know, whatever the truth is, like, yeah, whatever the true model that generated the data is, whatever shape it is, as I increase the complexity of the model, meaning the degree of the polynomial, I'm going to be able to fit that true data, the expected value of the data, better and better. So eta of x is some function. Eta of x is an arbitrary function, right? And Taylor's remainder theorem says explicitly how much error, if I fit a p-dimensional polynomial to any smooth function, how well does that error go down, and how much error is approximated? And it is a Taylor series, like the most fundamental concept in calculus, one of them, and it says that like as the number of terms in my Taylor series gets large under benign conditions, I will be able to fit that function arbitrarily well. Okay, and so that is the bias. The bias is really talking about how well can my expected function class, the expected function I learned, fit eta of x. Eta of x is an arbitrary function. As I add more and more complexity, meaning I add more and more degrees in my polynomial, I'm going to be able to fit eta of x better and better, whatever it is. So that's why the bias will always decrease as the complexity of the degree of my polynomial increases. So bias is sort of monotonically decreasing. Variance. So the reason why variance increases is with complexity is because if I have, I didn't save that slide. So, oh, that's fun.
Yeah, I think that's just a whiteboard app if you clicked on that. Is that what you clicked on?
I don't know, but this is fine. I just need a white space. So, okay, this is like the canonical machine learning picture. If I have data x, y, and I see data points like this, just like the picture that Jamie had, I didn't save that picture, then if I have a very low dimensional polynomial, I may be able to fit a function that looks like that. That's a pretty good fit. If I have a very, very high dimensional polynomial, I could fit these data points exactly. However, the degree, so this is like low p. And if I have a large dimensional polynomial, say high p, I'm going to be able to fit this data. You can look up in your linear algebra textbook why that is so, but I will always be able to fit each one of these pink points if I have a high enough polynomial. But that function could be crazy wild, right? Because this is a high dimensional polynomial. And so like this function is getting 0 training error. I fit the data exactly. But because I fit so many parameters, this is, this f hat of x is something like some parameter ak times x to the k. And if I have to fit p numbers from a very small amount of data, what can happen is that I'm going to basically be fitting noise. I think we can all agree that this orange line is a lot better than this green line. And so as you fit more and more parameters, you're basically chasing noise. You're trying to fit it, but like you're not really learning anything. You're really just shooting yourself in the foot. And that's why variance increases as the complexity increases.
So basically, bias corresponds only to the training data set that we picked right now, like suppose D1, but variance corresponds to like the behavior over different data sets picked. Is that right?
So bias is not a random thing. Well, that's a tricky way of saying it. Bias is expected with respect to the expected data set you would have seen. And variance is also with respect to data set, but it's basically, again, I'll put these little subscripts here. The variance describes how much is your function going to change with respect to the data set that you saw. So like with this data set, this pink data set, yeah, I fit it. Man, I fit that data set so well. But like from time to time, these pink points are gonna jitter a little bit and I'll get a completely different function. And so if I look at a particular point, if I say, hey, I'm really interested in estimating what the function value is at this point, well, for different data sets, I'm going to learn some different wild polynomial, and I'm going to get a very wild different prediction for each one. And that's what the variance is describing.
Makes sense. Thanks a lot, Professor.
Yes, Dalton in the chat is correct. As with large dimensional polynomials, just more parameters to fit mean more variance, typically. Okay. Now we will start.
One other question that's probably worth asking, or they're both. They're basically saying, is model complexity always decided based on the number of parameters and the degree of the polynomial? There are a couple questions that are sort of like this. And the short answer to that, which I'll let Kevin sort of expound upon, that is a good rule of thumb, but it is not perfect. Okay. We'll get more into like why that's not perfect in the next couple of lectures, but like more broadly, we'll talk about that throughout the class.
Yeah, I don't really want to go any deeper than that right now, but that's absolutely true. It's a good rule of thumb, but there's always exceptions, and we will talk about those exceptions as the class goes on. But for this stage in the course, I think the number of parameters is typically a good surrogate for the complexity of the class. Okay, so we just had this long discussion about bias and variance and all these expectations. And basically, if we look back at this, what did I tell you? I told the irreducible error requires knowledge of eta of x, so that's not computable. The bias also requires eta of x, which you don't know, so that's also not computable. The variance is basically with respect to your function, but you have to take an expectation over all data sets you could have seen, so that's not computable. So these three things, while they're useful for thinking about how to tune your algorithm, you can't actually measure any of them and give you actionable insight. So how do you actually think about what things you can measure? What is, you can only measure how your model performs on a data set. So what does that mean? And what does this phenomenon mean? Where I'm really sort of, this green function is fitting my data perfectly, but it's just a crappy estimator. We know that intuitively. What does that mean more theoretically? And so it's a concept of overfitting. So yeah, this is what I just said. More complexity has less bias, but has more variance. In practice, what do we do? So as we just said in this discussion, I'm going to assume that I have some classes of functions that are increasingly getting larger. So F1 could be, say, degree 1 polynomials, and then this could be degree 2, degree 3, 4, and so on. So basically, Fk, cal F sub k, is denoting all polynomials of degree k. Okay, and so at most k. And so basically one is enclosed in the other, and they're just getting more and more complex, strictly more complex. And this is just a model to sort of think about something. And so for each model class, FK, cal FK, I can talk about fitting a f hat k to the data that I see. Okay, because I observe some data set D, which are an IID draw from PXY assumed. And now for each model class, each model class FK for k equals 1, 2, 3, etc., I'm going to hypothetically fit a model f hat k to that data set. So I'm going to have a degree, the best model, the best degree 1 polynomial, the best degree 2 polynomial, the best degree 3 polynomial, etc. Okay, this is how I'm going to think of it. This is my mathematical model for thinking about bias variance and overfitting. And so what we're saying is complexity is going to increase as k grows, because we're assuming that each fk is enclosed in fk plus 1, meaning all k degree polynomials are in all k plus 1 degree polynomials. So what do we actually observe? We have a data set. For each k, for each fk, we compute our best model in class over this data set, what minimizes the error, the training error with respect to this model. And we can measure that. So now we have the training error. This is the training error of that f hat k for each k. So fix a k. For that f hat k, we have a training error. But again, like the last lecture, we don't care about the training error. What we really care about is the true error. How is this FK model going to perform on future unseen data? Or in other words, how is this f hat k going to perform on an xy drawn from the true joint distribution pxy? This is a future data sample. How well is it going to perform on that? That's what we care about. We care about the true error. But we can't measure that because that requires an integral or an expectation over the joint distribution of pxy, which is unknown, of course. So what do we do? What do we have? Well, suppose I could go and collect additional data. So I have some IID data set, my training set of this data set they gave me, but then you say, oh, by the way, I also have this other data set that's exactly, was collected the exact same way. They just forgot to give to you before. And so they're just from distribution, each one of these points in this test set is drawn independent, identically distributed, just like the training set. They are both IID draws from the same distribution pxy. Now what I can do is, given the f hat that I trained or learned using my training set, I can now evaluate it on my test set. Okay, so I have a training set, I fit my function f hat x to the training set, and then I evaluate it on the test set to get a test error. And so it's just the average error that I would have seen on a test set. And now you can show, because each one of these training points, each one of these test points was drawn IID according to PXY, the test error is an unbiased estimator of the true error, which is what we actually care about. And this is a problem explicitly worked out on your homework. So I encourage you to work through that. But basically, the test error is a good thing to look at because it is an unbiased estimator of the true error. If it is small, the true error is hopefully small. Because as the size of this test set gets large, we do expect, by the central limit theorem or law of large numbers, we expect that the test error to converge to the true error. But it's extremely important that the training error the training set and the test set are completely disjoint. There's no intersection with the training set and the test set. They cannot overlap. So let's make a plot to think about how the test error and the training error behave as the complexity k increases. So this is your degree polynomial is getting higher and higher. How would you expect the training error to behave? Right? Think about that for a moment. Think about this plot we saw a moment ago, whereas the complexity of the model gets larger and larger and larger, my degree polynomial gets higher and higher and higher. How do you think the training error goes down?
Decreases, yeah.
It decreases. Correct. So as the polynomial gets higher and higher and higher, the training error is going to go to 0. You're going to eventually, you're just going to be able to fit everything. You're going to be able to fit the training set exactly. And so as the complexity increases, your training error will decrease. But now, if we think about this picture again, how do you think the test error behaves? If we get some other IID samples, you know, it's like this. How do you expect that test error to behave? Right? Do you expect you're going to fit those functions really well as the complexity increases? Probably not. And so, at least intuitively, with a simpler model like this orange model, believe it or not, that's probably going to have a smaller test error than the green function, which is way more complex. Even though orange is a very low degree polynomial, it's sort of it's closer to those purple points that I just added, this test set, than the green function, which was wildly off because it was so trying to fit that training set so strongly that it just didn't care about what the function value was doing away from the data set that you saw to train. And this concept is known as overfitting, where you try to fit the training set extremely well at the deficit of fitting the function well at places you haven't seen, which will be characterized by the test error. And so this plot, this is a really cool plot. Each one, in here we know exactly what the model class is. Let's say we constructed our function class fk. We know what pxy is, and so we can exactly sort of completely construct what the training error is and what the test error is, because we know what the model class is. And so each little fine line here in red is basically one draw of the training set. So we drew some training set, and then we drew a test set. And each one of these fine lines is one particular path of the test error as the complexity increased. So for each fk, I drew a data set, a training set. I trained it and got an f hat k. Then I evaluated it on a test set that was also IID drawn and evaluated. And that's each one of these red lines. The blue lines is the same thing, but the training error. So I drew a data set D. I trained an f hat k on it, and I evaluated the training error on it. And that's each one of these little blue lines. And now the bold red and the bold red are the averages over all these samples that were taken. And so this is the expected training error and the expected test error, essentially. And what we see is, again, in expectation, these lines are not monotonic because real data doesn't behave how we would like it to. But in expectation, how we'd expect these things to behave is the training error will monotonically decrease, and the test error will start high, go low, and then get high again. Okay, there's some true bottom here, some best sort of error, which balances this bias and variance, but it is basically this is because the test error is an unbiased estimator for the true error. And so you're looking at the true error and you're seeing this bias and variance, but you don't get to see it. You only get to see the total error. And so this is the data that you can actually, what you would observe under any given one sample is just one of these lines. You'd just be able to observe the performance of f hat k on the test set, and you'd just be able to observe the performance on your training set. You only get one of these fine lines. And then from these fine lines, you want to pick the model class that has the lowest error on the test set. So, and I'll take questions in a moment. But what we conclude from this plot, though, one thing we conclude is that the blue line is always less than the red line, at least in this given plot. You will show on your homework that this is not a coincidence. In fact, you can show analytically that the training error the expected training error will always be less than the expected test error. This is a theorem. And it's very easy to prove. You'll show it on your homework. And so what we say is the training error is an optimistic look at the true error of your estimator. Meaning if you train some function f hat and you evaluate it on your training data set that you use to learn f hat, that's going to be very, very optimistic. Your error is going to be much lower than the true error of f hat. And the test error will be unbiased. And so whenever you want to evaluate your model f hat, you have to collect a new data set or have a separate data set you've never looked at, and then evaluate your function f hat on that test set. And that will give you a look at how well does the true error of your function perform. That's all this says. And so in practice, what do? In practice, you are given a data set. If your PI gives you a data set, say, hey, do some machine learning and learn some models. Well, what are you going to do? And also tell me how well it performs. So what you're going to do is the first thing you do is you're going to split this data set up into a training set and a test set. Okay, and you're not going to look at the test set. You're going to look at the training set and you're going to learn your model and pick you're going to look your data set. You're going to pick the model complexity K using just this training set. I'll tell you how in a moment. But you're going to just use the training set to learn f hat of K for each K, and then potentially the K hat that you're going to use. And then once you've learned some model, you've learned some model G that's going to be your output, only then do you evaluate it on your test set. Because that will give you an unbiased estimate of your error. So that if you go and train your f hat, then you're done with it, you're happy with it, you send it off to your boss, and then you say, okay, and your boss says, how well does it work? And then you're going to say, well, I'm going to evaluate on the test set. And then you evaluate on the test set, you get some accuracy out, and you return that to your boss. And so you should be thinking of, basically, when you were given data set, split up in a training and test, put the test in a safe. Put the test in a lockbox, give it to your boss. Your boss knows the combo, you don't know the combo, you don't get to look at it. You're gonna do everything you can on the training set, and then the true performance is when you look at the model together with your boss, he will then unlock the lockbox and evaluate your model, and you'll get some error, and that will be basically an unbiased estimate of how your model actually performs. And so the test error is the only unbiased estimator of your model. And if the test data set is ever used to influence the training of the original function, it is no longer an unbiased estimator. And so you can never, ever, ever use the test set to train your model. It is only for evaluation, because it is the only way to get a grasp on what is the true error. And I now realize that the slides stopped progressing, so that's awesome. Fortunately, I didn't really look. The slide isn't that interesting. It just says that. And we're done. So the natural question, though, is when you break your data set up into a training and test, how do you do that split? How big do you make the training set with respect to the test set? That's an excellent question. And it's a hard one to answer, honestly. We'll talk a little bit more about that when we talk about bootstrap sampling and cross-validation. But typically, it's a hard problem. And we will talk more about it. But typically, people break it up to, say, 10% of your test set and 90% training set. These are rules of thumb, but that's pretty typical of what people do.
And one quick comment. You said, how do you do that? How do you do that certainly has a size component. It also has to do with, like, how do you do that? Another, like, always, 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 never, ever, ever do anything differently. That split should happen randomly. It should not happen that you look at the data and you decide what goes in test and what goes in train. Absolutely not. It should be done in the most random, most like blind way possible.
So a quick question, Professor. So I get that the expectation of the training error is always less than the expectation of the test error. But
Yep.
if I fix a single data set, can I be sure that the training error for that data set will be less than the testing error?
No, no. This is, so you can see that actually in these curves, right? Sometimes these little the little red lines cross over the little blue lines. So for any given data set, it is not true, not necessarily true, that the test error is always above the training error. However, in expectation, they are. In expectation, the test error is greater than the expected training error. But on any given draw, you could have situations where the test error is actually a little lower than the training error. But these will be few and far between. That is typically not something we worry about that much.
Makes sense. Thank you.
There's actually little reason to ever look at the training error. Typically, you'd like to see the training error go down, but like really, it's not indicative of the true error. And so what you really like to do is look at the test error. The training error is usually thought of as like a lower bound on the achievable test error, the true error, but it's not altogether that informative. Any other questions? I'm done with content for today, so I'm just going to take remaining questions.
So I have one.
Go ahead.
If for example we have an intersection between the test set and the training set, then I assume that the test error is no longer an unbiased estimator of the true error.
Correct.
But mathematically, what's the reason? I can understand that intuitively, but
yeah. So what's going on there? It's a great question. So basically, you will talk a little bit about you'll go through these sort of calculations on your homework. But basically, if I take an expected value with respect to the random test set I could have seen, this is going to each one of these yi's and xi's are independent of this f hat. The xi has no resemblance and no dependency on the f hat, and that's why this is going to be an unbiased estimate of the error. If the xi's, any of these xi's, did depend on the value of f hat, I could no longer claim that this is unbiased, and this just goes to the fact that they're no longer independent, and just the expectation just won't work out. And that's really the simple end of it. Now, the next question you might ask is like, well, wait a second. What if I put like one training point in the test set? Does that ruin everything? Or said another way, maybe I put like some of my test points into the training set and every train. Is that really going to, okay, it's potentially not unbiased. Is that really going to hurt the accuracy that much? Is it really going to throw it off that much? Hard to say. That really depends on the model class. And it basically, if you do that, no one will take you seriously. Like it just, from a statistical point of view, it's so wrong and so bad to do that, that like, if you try to start telling someone a story that, well, I only put some of the test set into the training set when I trained, or I only used some of the test set to pick the polynomial, that's when people are going to start rolling their eyes and not really trust anything about what you're about to say. And so, yeah, you should not play games like that. The test set should really be locked away.
Thank you.
Can I have another question on the bias and the variance equation? Like in the equation, we have this bias part, variance part, and the irreducible error. Can you explain more on the irreducible error? Is that just mislabeling for y?
Good question. Okay, so the irreducible error, so eta, it really goes back to what is the definition of eta of x. So the definition of eta of x is how it's derived is basically you have some drawn x and y from this distribution pxy that you don't know. Now, if you fix a particular x, you can ask the question, what is the value of eta of x that minimizes this expression in purple, right? I'm going to take some random draw of y at a particular value of little x. And the question is, what is the value of eta of x? You have complete freedom in choosing this, it's just a scalar. What value should I choose in order to minimize the expected error? So there's no constraints on what eta of x can be. It can be an arbitrary function. There's no constraints. And so this is the best possible estimator of y in a least squared sense in expectation with a random y I could have seen. So eta of x is the best possible estimator that minimizes the expected squared error. And so because eta of x is the best possible thing I could have, the irreducible error is the error that is suffered by this best possible estimator. And the way to think about that is like, suppose the true value, suppose you're playing, I don't know, you're playing some guessing game, and I don't want to do that. Okay, let's talk about a coin flip, right? So the best estimator of a coin flip is going to be the bias of the coin, right? If a coin has a probability of heads being P, then what's the best least squares estimator of what coin flip you're going to see? It's going to be 0 or 1. Eta of x is going to be the value with, there's no x here, is going to be the value that minimizes the expected squared error. And that happens to be P. And so the expected, this irreducible error is basically the error of this best possible predictor, which is predicting P for the error between a 0 or a 1 that I could have observed. Is the best thing possible, but it's still going to have some amount of error. And so in math, what it's saying is that the irreducible error is basically just the squared error between the best possible thing I could do, eta of x, and the random y that I observed. So it's called irreducible error because you can't get any less. The way you define the eta of x was to be the minimizer of this expression. And so there's no way it can get any smaller.
Yeah, that makes sense. And also for the eta of x is based on the known x, right? Like for example, when in a row situation, it's only the training set.
So in this derivation, I fixed the value of little x. So I'm looking at a particular house. So a house that has 3 bedrooms, 2 baths, and 800 square feet. Given that little x, those parameters, there's many houses that could have those parameters, but I'm fixing those parameters. And now I'm saying, what is the best predictor of that housing price given those parameters? And that is the value of eta of x.
Yeah, I wonder the information of this house, has the information already been used to deduct has it already been used in the modeling process, or it doesn't matter?
It doesn't matter. So eta of x has nothing to do with your model. Eta of x is defined as the minimizer of I'll go back to this definition. Eta of x is defined as the expected value of y given x. Okay, that has nothing. There's no f in there. It has nothing to do with learning. Eta of x is the best possible estimator you could use, but we don't know what it is. And it has nothing to do with your model class. It just has to do with the actual underlying data, the distribution of pxy. And that is precisely why it is irreducible. We call it irreducible because there's no constraints on eta of x. It has nothing to do with your model class. And it's just something you can't get rid of. It's just the noise. It's the noise that you just expect to see in any given observation. For the same fact that like the best model in the world at housing prices, not every house, even the best possible model is going to have some deviation. you have the same exact house, the same location, same features, even the best possible model, not every house is going to be sold for that exact price. And that amount of variation is exactly this irreducible error.
Yeah, that makes sense to me. Thank you.
I have a question.
Uh-huh.
Yeah, so in practice, we only have a single data set, right? So how do we use these mathematical terms to, I mean, is it to gain confidence in our estimates, or how do we actually use it?
Yeah, good question. So just as you said, in real life, we just have a data set. Every single one of these terms, irreducible error, the bias, the variance, every single one of these requires a new draw of data from our data set to compute. These are not computable parameters. Why we care about them is because it allows us to think about algorithms. It allows us to say, if you observe some test error, that test error can be decomposed. The test error is an unbiased estimate of the true error. The true error can be decomposed into the irreducible error, the bias, and the variance. And so why we talk about bias and variance is because if you observe a large value of the test error on your model, the thinking about bias and variance allows you to think about, it's a thought experiment, and say, well, look, because my test error is high, the error is either coming from the irreducible error, the bias, or the variance. And now you go and think about your model. Well, maybe I can do something else to get a handle on what is the irreducible error. What is the smallest possible error that I could have? And then you think like, well, is my model very complex? Am I using like a really simple sort of low degree polynomial? Well, in that case, maybe the problem is not that maybe my model is not complex enough. Maybe on this curve, the bias is dominating. And so maybe I should try a larger degree polynomial to minimize this, to reduce this bias. On the other hand, if you're using a huge deep neural network and you're getting a large test error, well, that could be two things. Either your bias is high or your variance is high. But if your model is really, really high dimensional, tons of parameters, it's probably too complex. It probably has too many parameters. Your variance is too high. And so what you want to do is reduce your variance. And so we'll see examples of when we talk about the bootstrap to actually talk about these kind of parameters and how you can get a handle on some of these sometimes. But a moment ago, I said the training error is a optimistic look at what your true error is. Well, because we know as the training error, as the complexity gets very, very large, the training error goes to zero, right? Or it gets smaller. But yeah, I mean, like it's always going to be a lower bound on your true error. I mean, I don't really want to say more than that, actually.
Okay, all right, thank you.
Yeah.